We were right at the threshold of the algorithm yesterday. We showed that the range minimum problem and the lowest common ancestor problem are very much related. They're linearly reducible to each other. And so we said that now, since we haven't seen an algorithm for either of them, we're now going to see Omer Berkman's algorithm for both of them together. So we start by a range minimum algorithm. The pre-processing is going to be O of n log n, and the query time is O of 1. This is almost where we want to be because we want the pre-processing to be linear time and not O of n log n. Now, some people say that we're being petty and quibbling about the log factor, but we do. We quibble about log factors, and sometimes people even quibble about they reduce from log n to log n over log n, and they're excited about that too. So yes, we care, but we'll start with that anyway, and we'll see that in order to solve this range minimum problem this way, we are actually also going to use a special case of a lowest common ancestor. So we will be using an LCA algorithm in order to solve this, but a very special case of an LCA algorithm. Afterwards, when we have this, we're going to need to go down to O of n, and we'll see how we do that. So what is the story? We have an array A1 through AN, and we want to do a range minimum algorithm. So let's construct a complete binary tree on top of A. So again, if your numbers are such that it's not a complete binary tree, it doesn't matter, because in the big O, even if you pad it with up to the latest, up to the closest power of 2, it's still not going to be more than twice as big. So in the big O, you're not really losing anything. So let's assume now, for reasons of exposition, that everything is fine, that we are a power of 2 and we have a whole tree. Again, as we know, this in algorithms, this is not generally a problem if it's not a power of 2. So we have a complete binary tree on top of it. That's where you get the n log n, actually, because you now have a binary tree. And the tree has log n height. Now, for every node in the tree, we're going to do the following. We're going to write a little bit of information. I mean, the tree itself, obviously, because every level is a half of the level below, so the tree as it is not in itself n log n, it's only O of n. But we're going to write information on each one of the nodes, and that's what's going to make it a bit bigger. So for every node in the tree, we're going to look at all the prefixes of the leaves and all the suffixes of the leaves. And for each prefix, we're going to write the minimum, and for each suffix, we're going to write the minimum. So let's see the picture that explains it completely. So we have a tree, and these are the leaves of the tree. Okay, so the prefixes are A1, A1, A2, A1, A2, A3, A1, A2, A3, A4, etc. So we're going to actually write down the minimum of the first prefix, the minimum of the second prefix, the minimum of the third prefix, the minimum of the fourth, fifth, up to the last prefix. So that's what we're going to write on one side. On the other side, we're going to be considering the suffixes. So we have the entire suffix, and we're going to write the minimum of the entire suffix. Then we have the second suffix, we write the minimum of that. The third suffix, the minimum of that, etc., up to the minimum of the last suffix. So this is the information that we're going to write on every node of the tree. Now, why do we need this information? Because remember, the bottom line is that we're going to want to we're doing range minimum queries. So here we have a bunch of minima already. So if we get to this node and we need the minimum of one side, then we go to the appropriate minimum that is already written. And so the idea is that whenever, again, so let me try to draw the intuition. So we have this tree, and if we want the range minimum of some range, then basically we're going to go to the LCA of that. And then at some point we're going to get, so we need some suffix here. Sorry. Yes, we need some suffix here, and we need some prefix here, and that's what we're going to get because we actually wrote all these things down. So we get it in constant time. And that's where you see also where the LCA is going to come in, because now in this tree, we are going to find the LCA of the two nodes, and that will aid us in our solution. So let's look here at a full example in order to internalize what we've just said. So our array is on the bottom, 10, 1, 2, 9, 3, 8, 7, 6. That's our array. And this is the complete binary tree on top of that array. In the very bottom, we can assume that I wrote it only once, but if we want to generalize, then really you have 10 on one side, 10 on another. And then in the top, you have 10, 1, because the first prefix is this one. And the smallest number of that prefix is obviously 10. So we write it 10. The second prefix is 10 and 1, and the smallest number is 1. So we write 10 and 1. On the other hand, as far as the suffix is concerned, the largest suffix is 10, 1, so 1 is the minimum. And since 1 is the minimum altogether, that's also the minimum of the second suffix. Here with the 2 and 9, similarly, we have 2, that's the minimum, and 2 is also the minimum of 2, 9. 2 is the minimum of 2, 9, and 9 is the minimum of 9. And so on for the 3, 8, and the 7, 6. Then if we go yet one level up, at this point, you can see that the first prefix is 10, so that would be the minimum. The second one is 10 and 1. Then 10, 1, 2, and then 10, 1, 2, 9. But in all of these last three, the 1 is the minimum. So that's what we write. And as far as the suffixes, you start with the 1, then you have 1 again, because we're now looking at this suffix, then 2, then 9, and so on. Now, I'm not going to go into the detail. That's something you can figure out for yourself, how you can actually use this information in order to build this information. You don't need to always go all the way down and construct the information. You can use whatever you have at hand in order to construct the ones up. That's a little exercise. But that can be done. And then we have this entire tree. Now, at this point, we want to know the size of the tree. Now, we said that the number of levels is log, and in fact, but in each level, we have half of the number of nodes. However, in each level, we also write twice as much information on every node as the level below. So our information is O of n, really, at every level. And therefore, we, in fact, have a n log n space here and not linear space, even though the tree has a linear number of nodes. But we keep writing more and more information on every node on the way up. So that's what gives the n log n blow up. So if we want to actually add it up, so the size of the tree we have on level 0, that's the leaves, is going to be, I guess I'm not consistent with these things, but it depends on what paper you read and what they call the level. So on level 0, we have, that's the leaves. We have 2 times n. Then on level 1, we have twice as much as we had before. So we have n over 2. We have n over 2 nodes. We have 2 elements written on each side, and we have 2 sides. So it's 2 times n over 2. In the next one, we have n over 2 squared nodes, 2 squared information on each side, and 2 sides. So as you can see, we can cancel out these 2 to the I on every side, you end up with an n. Altogether, for log n levels, 2 times n information, and that's the total size of the tree, O of n log n. Now, in fact, we can also compute it in time O of n log n. As I told you, as I left a little exercise, you can always use the information below and construct the information on your level. Use the information from below and construct the information on your level. So the time is O of n log n because you take O of 1 time to construct the data, each one of the datum. Okay. So now, how do we do a query computation? This is all we need. We have this tree, and we need to do a range minimum query of I and j. Okay, so the first thing is we find the lowest common ancestor of I and j in the binary tree. Okay, so here we're using the lowest common ancestor in order to solve it. And we'll soon see how to do it in constant time in this tree, because remember, this is not a general tree. This is a beautiful binary tree, full. So in fact, finding the lowest common ancestor in something like this is quite easy. Once we find the lowest common ancestor, we're going to go to the left sun and find the minimum in the suffix that starts at I. And that you can do in time O of 1, because all these suffixes are there. So you don't need to compute it. You go to the left, you have the suffix that starts there. Then you go to the right sun, and you find the minimum of the prefix that ends in j. And between the two of them, they cover the area, because that was the lowest common ancestor. So you take the minimum of those, and you're done. So the minimum of the two gives us the answer. What does it have here? Yeah. So let's look at, we'll go to our example and look for something and see how it's done. Make it smaller. Oops, no, not that small. See, that's why we don't scale down, because you scale down to a point. Okay, we make it smaller, and we'll move up the See, I've been spoiled by this. I'm going to go back and my moves will be off, because in Bar Ilan, I already figured out how I talk about the next thing while this is moving up, and then I will have forgotten this. Okay, so I'm going to move this a little bit. Another arrow. Okay, so suppose we want the range minimum of, you know what, let's do it like in the games and in the magic tricks. Does anyone from the crowd want to give a range? What should we try? No one wants to give a range. Fine, so we'll do it from here to here, let's say. Okay? But this way you think that it was rigged. If I ask the crowd and someone says, then you know it's not rigged and everything works. Okay, so we want from here to here to find out what's the minimum. In fact, so we see that the minimum in this range is 3. But let's see what we're going to do. Well, the first thing we need to do is to find the LCA of 9 and 7. So the LCA of 9 and 7 is, in fact, here. So both of them are in this tree. That's the lowest common ancestor of the two of them. So now, what it means is that if we go down to the right and if we go down to the left, the entire range has to be between some suffix of this sun and some prefix of this sun, right? Because that was the, so since they are all here. This is a binary tree. So half of the not half, but part of the range is the part that's in this subtree, that is a prefix of the leaves of this subtree, and the other part of the range is a suffix of this subtree. So okay. So as far as that goes, the intuition is clear, and so, but we even know what suffix we're talking about, because since the 9 is here, it's this suffix, and then the 7 is, we're looking at the prefix. The 7 is the third prefix, it's right here. That's the 7. So between the two of them, we have to take the minimum of this suffix and of this prefix. And since this is 3 and this is 9, then the minimum that we're looking for in the range is 3. So it works out very nicely. There are two things that we need to see. And one is how to do the LCA, which we're going to see in a minute. But another thing that I will also leave as an exercise, and it will be an easy exercise after you see how we do the LCA, is to actually figure out which one of these guys is the one that we want to look at in constant time. But it's clear that it's going to be some arithmetic computation, because you know what you're going to get really is not a 9 and a 7. You get indices. So you have to get the index and compute which suffix it's going to be of this in the subtree. And so once you compute what suffix it is in the subtree, and it is going to be an arithmetic computation, you go exactly in time O of 1 in the array of the minima to the position you need to go. So in time O of 1, you compute which suffix it is and which prefix it is, and then you take the minimum of the minima. Let's look at one more example, and then show how we do the LCA. Okay, so does anyone want to give a range now, or still not? I started the first day, I gave you a beautiful Hebrew saying that Lo Abaishan Lamed, which the one who is timid or shy is not the best, does not study well. It doesn't. Shyness does not contribute to good studying. So come on, somebody give me a range from where to where. I give up. Okay. 10 to 9. Ah, yeah, you pick an easy one. Fine. Okay, she did it, not me. I don't make life easy for myself, generally. So we want this range. What's the LCA of these two of these two? If this is I and this is J, so in fact it's 1, 2, 3, 4. So what we want is the range minimum of 1 and 4, between index 1 and 4. So we go to the LCA of 1 and 4, and it's this one. And then the question is, and then we go to the left son and the right son. So we know that the minimum is going to be some suffix here and some prefix there. But in this particular case, because it was 1, so the suffix is going to be this one. The suffix is going to be this one. And in the other one, we're going to have a prefix that's everything, so it's going to be this one. The longest suffix and the longest prefix. Okay, the minimum, 1 is 1 and 1 is 2, so the minimum of them is 1, and we're going to say that this is our range minimum. And indeed, that is the range minimum. So everything is working according to plan, and we got the appropriate answer. Okay, so our pre-processing was O of n log n, and as you can see, every query is O of 1. The one thing that I still owe you is how do we do the LCA? Because that was part of the question. I mean, the whole thing started because we said, how can we were looking for an LCA algorithm. So what have we done? Okay. Size of the tree we saw, query computation. Okay. So what we need to now find out is how do we find LCAs in a binary tree in constant time? Now, what I'm happy here is because it gives us a chance to again consider something that we have mentioned before about the model of computation that we use, that we're looking at the random access model. And as we had mentioned before, in a random access model, when we count the work is in word operations. And our words are generally of length O of log n, where n is the input that we deal with, because otherwise we cannot even grab our information in time O of 1. And we cannot do any operation in time O of 1. If we're going to look at bit complexity, then you have to look at if you multiply two numbers, then you have to look at what is the bit complexity of number multiplication. Which, by the way, the interesting thing is that in hardware, numbers are not multiplied in a theoretical optimal way, but rather in in something that works in hardware, but theoretically is actually quadratic, even though it works faster. Because if you think about it, the big problem, if you're doing bit operations and you're trying to construct a circuit that is going to multiply two numbers of m bits. So in your circuit, okay, you can multiply the bits, but on the other hand, if you multiply bit by bit, you're going to have the carry, and the carry needs to move, and sometimes it needs to move all the way. And so if you do it serially, your time is going to be O of m when you're looking at m bits. But obviously, you don't need to do it serially, and you don't, because since it's a circuit, so all the bits are multiplied together. But now the question is, how does the carry propagate? And one of the ways, or the theoretical way to do it, would be to actually do something similar to what we did here, and that is to construct a, so you have all your bits here, and you multiply these bits by these bits. And the question is, how does the carry propagate? So you can do a binary tree here and use that to propagate the carry, okay? So you're going to have m log m in order, or log m, because that's the height that you need to propagate the carry. It goes up and down appropriately. However, that is not how they do it. What they actually do is something else. When they construct that circuit from an engineering point of view. So actually they have, oh wow, this thing is completely broke. Well, fortunately there are others. So what they do is they have I felt that these are the good ones and those are the bad ones, so we'll see how it goes. Excellent. So what they have is is basically a line going through, and on that wire you send a 1, like as if that's the carry. But whenever that needs, but locally, whenever that needs to be broken, you break it. So that's how, in fact, they propagate it. Now, everybody knows that the speed of electrons on a wire is actually quadratic. It's quadratic in the length. But it is so much faster than doing the computations of the tree that in those sizes, that works faster. So this is an example of when constants play a role. So the constants of the quadratic algorithm are actually better because we're talking here about so many bits, and so the distances are very small. At that point, the quadratic in the distance is better than to start doing the computation. It's one of these little things in computer science that someone like me who is a theoretician shouldn't even know. But in another life, I actually used to sit under the computer with a scope and look at all kinds of things happening. So it was interesting. So again, so now the whole thing was because we're looking at the word arithmetic. So we have a word of size log n. And the arithmetic of that word we actually do in O of 1 time. Because, like I said, every such word actually has, in hardware, actually has parallel mechanisms. So the whole thing is assumed to take O of 1 time, the word arithmetic. Okay, so having said that about the model, and it's an important thing to consider, it really is, because somehow the first time someone sees this, if they don't consider, they think there's cheating going on here, but there isn't really, because our entire complexity analysis that we do from year 1 data structures and on, and it never ends, when you're in a random access machine, that assumes that you indeed handle a word in constant time. Okay, so we're looking at a binary tree, and that's what's so nice about it. We said everything here is we're a complete binary tree, and if we were looking at a binary tree, you can always give a name to every node. This is also a known trick for dealing with binary trees. You can give a name for every node that actually denotes the path to get to that node from the root. So if you go left, it's a 0. If you go right, it's a 1. So to get to this node, it says 1, 0. So you go right 1, left 1, and you got here. You want to get to this one, it says 1, 1, 0. Right 1, left 1. So the names in a complete binary tree, the names that we can give are actually the binary encoding of the number even of the node. But it tells you on the tree how to walk in order to get there. Now, the fact that it's a binary encoding of the node is very nice, because that means that we're not using more than log n bits, which is our word size. So that's wonderful. But the thing is, now if you look at it, if I take this node and this node, can I compute by the path? Can I compute the lowest common ancestor? So I have two nodes, this one and this one. I always went like that in order to compute the LCA, but that's O of the height of the tree. But I'm trying to say is that just doing some arithmetic operations on their numbers should be able to tell me the lowest common ancestor. Because who is the lowest common ancestor? It is the node that you go down to for both of them the same, and then they split. Okay, so if I have 0, 0, 1 and 1, 0, 0, so to get here I need to go to the left. To get here I need to go on the right. So I know that already on the bottom I split. On the other hand, this one and this one, well, I go left for both of them. Then this guy goes left and this guy goes right. So where would the lowest common ancestor be? This 0. Okay, so in general, if you look at these numbers and you say to yourself, what's the formula? Well, it's the longest common prefix. So take two numbers and their LCA, the code of their LCA, the name of their LCA, which in fact, because these are numbers, so you can have, once you know the name, and since all of these are sequential numbers, you can have these lists of pointers. So you compute the number, you go to the pointer, and smack, you're on the LCA. Not a big deal. Everything is going to be O of 1 once you compute the longest common prefix. But these are log n bits. And how do you compute the longest common prefix? With arithmetic logical operations. Do an exclusive OR, and the number of zeros, of leading zeros that you have, is going to be exactly the length of the longest common prefix. So all you need to do now is to shift everything, so what's left is just the longest common prefix. So you shift log n minus the... Yes, okay, so it's actually written down. So so first of all, does everyone agree that the LCA of ij is the longest common prefix? Okay, so now we need to find the longest common prefix, and we need to find it by logical and arithmetic operations on I and j. Okay, so let's look at these two guys. We have 0, 1, 0 and 0, 0, 0. What's the longest common prefix here? It's this, because this one has a 1 and this one has a 0. Now, if we do an exclusive OR of these, then as long as the numbers are the same, we're going to get a 0. The first non-zero number that we get is going to be where they split. In other words, for these guys, 0 is the LCA. So how do we get this 0? All we need to do is actually shift this thing right by the bit in which the leftmost one exists in. Okay, so exclusive OR we can do in time O of 1 because this is a word. So in time O of 1 we do the exclusive OR. How do we find this one, this leading one? In fact, it's the floor of the log of this number. So log is an arithmetic operation, floor is an arithmetic operation. All these things we do in time O of 1. So take the floor of the log, which in this case the log is going to be 1, so it's always shifts, right? So you need to add the 1, which means that there's a mistake here. Make sure that you realize that. So you do a log of this thing, and then you shift, and you got your number. So LCA basically is taking the log of XOR ij plus 1. So you shift I to the right this number of bits, and truncate. Truncate means that, in fact, there should be zeros here, but this actually tells you what height you are. So you know how much you truncate according to this, what height you are. There's another trick you can do, is put like 2 1s at the end of everything. So these 2 1s are going to tell you what height you're at. But basically, because, I mean, what I'm trying to solve now is this conceptual problem that what is the difference between 1, 0 and 0, 1, 0? In a word, you're not going to have this truncation. So somehow you need to know where it is. So you need to know either what height we are, or to actually put like 2 1s always at the end, or telling you, okay, this is the end. So all the other zeros don't really exist. So some convention in order to tell you where you are. But again, we are now looking at all kinds of implementation details that are clear that can be done, and so we don't care about. So here, so we found in just by using a couple of arithmetic operations and then doing shifts, we can do it. So here's an LCA in a binary tree. LCA is very easy because because all these nodes have names, and we can figure out the name of the LCA. So that's pretty. And we now, with that, we conclude. Well, with that and this exercise here, a similar constant time mask allows finding the index and the min prefix and min suffix of the LCA in constant time. Exercise. Similar kind of thing. So we did what we wanted. We have now a range minimum query pre-processing n log n, which is the interim step that we promised. And the queries are in time O of 1, which in fact allows us in time O of n log n do and query time O of 1, also do a general LCA. Because we saw yesterday that if you know how to do range minimum queries, you have a linear time reduction to the LCA. So we're almost there. So now the remaining problem is getting rid of the log factor. Yes, I didn't use it yet. We're going to use it now. Okay, so what we did now was our O of n log n of range minimum used the special case of LCA, which we showed how to solve. And that in itself gives an O of n log n to a general LCA. But now we're getting rid of the log factor. We're going to eventually get to the fact that we need to get rid of that we need to make use of the fact that our range minimum queries are really very specialized. Everything goes one up or one down. We don't have wild numbers floating around. So yeah, we haven't done that yet, but it will play a role in the future. In the near future, even, I should say. Within the next 2 days, we're going to... Okay, so what's the idea? And by the way, this idea is one that is a very common idea or was a common idea, because people don't really do PRAMs much anymore. But at the time, it was a very common idea, because remember when I explained to you about the PRAM, the parallel random access machine, and I told you that an optimal speed-up algorithm is one where the work, meaning the number of processors times the time, is equal to the best serial algorithm that is known. And if you have a lower bound, then that would be really optimal. But in any event, the speed-up is optimal if you're going to if the work is equal to the serial speed. Now, in a case like this, our time is O of 1, and if we assign O of log n processors, we can actually do the processing also in O of 1, but the work is going to be O of n log n and not O of n, which is what we want the serial algorithm to be. So the trick that I'm going to show you now was a trick that they used many times. So they say, okay, I don't have optimal speedup because I now have the log n. So let's now look for a coarser version of the problem where I have n over log n information. And so at that point, if I have n over log n, my work, even if I reduced my problem to n over log n information, then at that point, n log n is going to be n over log n over log n is n. Okay, so the work is really going to be O of n, but then I need to show how I can fix it up and take care of the small details, which again reminds us of a technique that we saw with the Abramson-Kosorajo algorithm. So you're beginning to see repetition of techniques, and that's part of the bag of tricks that an algorithms person has. He has this bag and he sees an algorithm and he starts taking out the tool. Does this work? Does that work? And something has to come out, or smoke comes out. Okay, so what we do is now we'll divide the array into n over log n substrings of size log n. Okay, so we divided the array, the big one, this way. And for each one of the n over log n substrings, we're going to find the minimum. So that's you do in linear time, because you just run through the entire thing, and for every one of them you keep the minimum and write it down. Keep the minimum and write it down. So finding a minimum is O of n. So linear time, you can do both the division and the minimum for each one of the log n's. But at this point, we now have, if you look at the array of minima, we now have an n over log n array of numbers, and we want to pre-process that for range minimum queries. So we have an algorithm that knows how to do it in time n over log n over log n, which is really n, because log of n over log n is log n minus log n, but the minus log n is going to be lost there, and the logs are going to be canceled out, so you get O of n. Okay? So we construct the full binary tree for finding the range minimum of these log n numbers. And the time and space, as I said, is O of n over log n times log of n over log n. So that's O of n. Good. But now, query processing. I'm getting I and j. And so let's assume for the moment that here's I and here is j. And we want to know what is the minimum in this range. Okay, so let's do a range minimum query over all of these log n size substrings. We have these minima here. So the minimum of them is going to give us the minimum in this range. So that we can get in time O of 1. Now, in time O of 1, we're going to find the minimum of this suffix. And in time O of 1, we're going to find the minimum of these prefix. We now have 3 numbers. And so we choose the smallest of the 3. And that is going to be the minimum from here to here. So that gives us the solution. But please tell me, how do I find in linear time the minimum between here and here? I need to run over them, so it's like a log. It's not linear. I mean, yes, the thing is small, but I still have a logarithmic amount of running to do. So in order to help you think of the answer, let me remind you of something else. I'm asking you, how do I find, and I'm assuming that you're going to run to find it every time you need it. But every time you need it is a query. Is there some sort of pre-processing you can do that will allow you, the pre-processing is linear, and that will allow you in time O of 1 to find the minimum here and here? Or let's just concentrate on this. The other side is symmetric. Okay, so now, again, think. The problem that I'm presenting with you is the following. You have an array of length n, and we divided that into n over log n substrings, each one of length log n. Wonderful. I want to pre-process this entire thing in time O of n, such that afterwards, if I give you a substring number, so this is the third substring, and if I give you an index in that substring, you'll be able in time O of 1 to tell me what's the minimum in the suffix of that particular substring. Okay, so I'm fixing one of them at this point. Okay, how do I know the... So I know that I'm in this string, and I want the minimum in this suffix in O of 1 time. How can I know it? Yes, we pre-process it. Good. What do we want? Yes, you want to construct some array of what size, or some table of what size? Of size log n, right? Because we're looking at that string. So she's saying, consider a log n string. We have here this string. This is log n. So we're looking at this log n string, and we want to find, pre-process it in time O of log n, okay? Such that when I give you an array, when I give you an index, you'll be able to tell me what's the minimum here. So we pre-process that, and we build a table. What table are we going to build? The table that says this is this minimum, The table that says for every I, what's the minimum in that substring. So this will give the minimum here, and this location will give the minimum there, and this location will give the minimum here, and so on. And how do we do it in linear time? We start from the right, and we say, okay, the minimum of this substring, let's give numbers. 1, 5, 10, 2, 11, 13, 1, 7, 3, 8. Okay? So we're going to build this table. We start here. What's the smallest number in this substring? It's 8. Okay? We add another number, 3. What's the smallest number in this suffix? Well, it's going to be the smallest number in this suffix, the minimum of the smallest number in this suffix, and 3. Since the smallest number in this suffix was 8, and 3 is the new number and it's smaller, so it's going to be 3. Okay, now we get to 7. What do I write here? It's going to be the minimum of the smallest number here and 7. Well, the smallest number here was 3, and 7 is bigger than 3, so we still have 3. So we move over one more. 1, the minimum of 1 in this suffix is 1, because 1 and 3, 1 is smaller, so it's 1. Now the 13 is bigger than 1, so the 1 remains. 11 is bigger than 1, so 1 remains. 2 is bigger than 1, so 1. 10 is bigger than 1, 1. 5 is bigger than 1, 1, and then 1. Okay, so this is going to be the array that we constructed, and we constructed it in linear time. It's a linear size table, and we constructed it in linear time. And now, when you come up and you say, give me the minimum between I and the end, you say, fine, I'll go to that table that I did in advance, and I find the minimum. So now, indeed, we have this minimum in O of 1, this minimum in O of 1, and this minimum in O of 1. So we're done. Are we done, or is there still some case that we missed? Yeah. So everything is good, except for one thing. What happens if I and j are in the same substring? Okay. So how we find the minimum? In the pre-processing, we write the minimum of every prefix and suffix. We put it in a table, O of n pre-processing, and constant timetable lookup. So it's written here. And so the remaining case, as we said, is when I and j are in the same subarray. Log n, I and j. Oh no, we worked so hard. We thought we were done. But we're almost done. So, well, let's use the same technique as we used for n. So we're going to divide the log n into log n over log n pieces, each of which pieces is going to be of size log n. And we're going to do what we did before. So everything that is not, okay, so look, it's just, we multiply the work, but it's still, so linear time pre-processing, and in time O of 1 we get it. And now we can find the range minimum of anything that is not with distance log n from each other, because that's the size of the small sequences now. They're of size log n. So we still have a remaining problem, and that's to find the range minimum ij within a subarray of size log n. So it's getting smaller. Obviously, you can do it again and get size log n, but we got to end somewhere, because otherwise you're going to end up here with log star. And so yeah, you can have a log star n query, which is very, very close to 1. I told you about the Ackermann function, right? What I did to the first year students. So Yeah, log star is very tiny. It's close to 1. And you could be satisfied, but we're not, because we actually want it to be O of 1. And also because we still have a piece of information that we didn't make any use of, and that's the fact that going up and down is only one step at a time. All right, so finally we get to the important fact that the range minimum queries are on a restricted array. And that array goes up and down 1. So now let's take every log n subarray that we have and normalize it. We'll normalize it in the sense that we say, okay, here is the number where this subarray starts, and then we're going to have a binary array saying whether you go up or you go down. Okay? So it's a one-to-one correspondence. So we're going to have, well, here I said -1, 1, whether you go up or down, but it doesn't matter. It can be, it's a binary array where you have a number that says, here's where I start, and then you say, I go up, I go down, I go down, I go up, I go up, I go down, I go down, I go up, etc. Now, let me ask you the following question. Okay, so why do I say that it's a unique way of describing it? Because let's say that we have the array. Oh, those were the ones that didn't write, yeah? So we have the array that was 3, 4, 5, 4, 3, 4, 3. And then we had at some place 96, 97, 98, 97, 96, 97, 96. Now, we're going to be able to represent this by writing 3, or the first position is going to be 3, and then say +1, +1, -1, -1, +1, -1. And here, we're going to represent it by writing 96, +1, +1, -1, -1, +1, -1. Now, if I give you this array, then you know where to start, and the plus and the minus are going to tell you how you're going to write the rest of it. So if I represent the array rather than like this, I represent it like this, it doesn't really matter. Okay? Agree? So I can represent it anyway. But what do I gain by this representation? What I gain by this representation is the fact that this one and this one, this one and this one are really different arrays. However, because in their representation, other than the first number, they are actually exactly the same, the range minimum is going to be the same index. So what's the minimum of this one? It's 3, okay? You can write it here, you can write it here, you can write it here. But the minimum of every subarray that you take, any range that you take, the minimum is going to be the same in both of them. So if you take this range, the minimum is this index. And if you take this range, the minimum is this index. Because they go up and down the same way. Where they start, it doesn't matter. Because you're not doing now the range minima relative to other locations. Relative to other locations, we already know how to do it. But we're doing the range minimum within this little subarray. So the range minimum in this subarray is exactly the same index for both of them. So what does it mean? It means, and this is like epiphany. So two subarrays have an equal normalized template, have the same results in range minimum queries as far as the index is concerned. So given a template and an initial level, we can construct the initial subarray. So all of that is good. But here is now the crucial fact that yes, there are n over log n such subarrays. But how many of them are truly different? Only 2 to the log n are different, which means we only have log n templates that are meaningful. So no matter how many of them we have, but the number of templates that we have, that are meaningful, there's only log n of them. So compute by brute force the range minimum for each one of these log n templates and write it down. Write down a table that's log squared n. So you have now log n tables. Sorry, you have what am I talking about? Log n squared. So you have, so if I want, this is log n, okay? And if I want to, for every range, pre-compute the minimum, it's going to be in a table that's log n squared. And I have log n tables like that. So it's log n times log n squared. So this is the time and the space that it takes me to pre-compute all of these tables. Now, log n times log n squared, is that less than linear or not? It's obviously less than linear, so do it. What do you care? All right, so now you're done, because you have the mechanism to give you the range minimum queries whenever what you're looking for is not within a block, a small block, a log n segment. Okay? And if your range minimum question was within a segment, then that segment, pre-compute for each one of the segments. You can use tries, for example, to do that. Pre-compute for each one of the segments what template it is, go to the appropriate table, and write the range minimum in time. So the pre-computing is O of n was initially, but now that you know that your I and j is within a particular segment, you know what template it is. So in time O of 1, you go to the appropriate table, find the ij, and write the minimum. You have the index, so go and find out what it is and write the minimum. Which means what? That your time is now O of 1 for all cases. So what you need is well, you have log n squared for each one of the segments. You have log n segments, so that's the space. But yes, you also need an array of length n over log n in order to tell you for each segment what template it has. When the I and j are in different blocks, that's what we, yes, so that we handled before. So yeah. But here it is. So now we have a range minimum algorithm whose pre-processing time is O of n, and the query time is O of 1. Obviously, that means that now we can do LCA like that, but you saw how we use special cases of one and the other, and at the end, and this is a neat trick also to remember when it comes to algorithms. So at the end, sometimes how you count something is important, because if we counted from the side of n over log n, there was too much, and we would have gotten in trouble. But then we said, okay, so count now from the other side. How different are they from each other? And so if they're not that different, if you can divide them into groups that are, into a small number of groups that are similar, and you can do this division and this identification fast, at that point you gain. And that's the trick that we used here. And this is the end of Berkman's algorithm. So what does it say for summary? The total table size we said. So for every I and j in a subarray, we look up the, yeah. And that's the end of the algorithm. Any questions on this algorithm? Yes. could we use bit operations to find the range minimum rather than having it at a table? I doubt it, because if that were the case, you wouldn't need the entire mechanism. You could have done that on the entire array, because the entire array has that property. So I don't think so. It doesn't, and it doesn't seem like it doesn't jump out. Yes. I don't know if it seems reasonable. I don't know what reasonable is, but it doesn't jump out as something trivial anyway. So if something like this exists, that would be a very nice new algorithm for range minimum. So okay. So at this point, what I want to do is, so we learned a whole bunch of stuff. And what I want to do is use a lot of the things that we learned, show you how different uses of some of these tools can help in various ways of solving a problem. And we're going to see a bunch of possible trade-offs here. And so I was looking around, and this particular paper ended up being a cute one because it has in it really uses of the LCP and the suffix tree and the LCA and range minimum and the whole, actually, bunch of other things that are similar, and I'll be able to describe what they are as we go along. But it really shows a great use of these tools that we've seen and how to solve a new problem. And really, when you're looking at research, so a lot of papers, the way that most papers are what people call incremental. What does incremental paper mean? As someone said, you stand on the shoulders of giants. So here is the frontier of our knowledge, and we increment it a little bit. Now, it may be that the way that we incremented it in itself is not any novel way, but it meant that we sweated a lot, and we used a lot of knowledge that was garnered and gathered along the years. And so we managed to pull it all together and move another step. And then there are the times when you have a completely new idea, a completely new technique. Those are groundbreaking results. Those are really the rare ones. And my PhD advisor used to say that the 300 years from now, who is going to be the computer scientist whose name is going to be remembered? Those will be the ones who did like the groundbreaking stuff. But it doesn't matter, because we're in this world not to do groundbreaking stuff. We're in this world to increment. If every one of us makes it a little better, then we're moving positive way. So that's the idea. So this particular paper, as you see, has a lot of names, because a lot of people, we just sat together having fun, and we looked at the problem and started throwing around ideas, and ideas gave different kinds of results. And finally, there was one new idea at the end. But so we'll see that also. But what I want to actually stress here is not even the new idea that is going to be at the end, but rather even the use of all these techniques that we've seen for getting new results. So what was the motivation at all? So longest common prefix, computing that, we know that it's very useful. We used it even in this algorithm before to compute the LCA in a complete binary tree, but we used it for the fast edit distance algorithm of Landau and Vishkin. Longest common prefix is used in Lempel-Ziv compression. And in fact, so you can use suffix trees and LCAs for doing Lempel-Ziv compression. Longest common prefixes are used a lot in biology. When you do tandem repeat, sequence alignments, all kinds of problems they have in biology, they use the longest common prefix problem. So it's something that is used a lot. We have used it, and a lot of people use it. So there are algorithms that know how to do it. But there were generalizations. In 2005, a paper by Kormod and Muthukrishnan, they considered the maximum LCP between a point and a range. So here I have a point, and I want the largest LCP that I can get between this point and any point in this range. Okay, so we want max LCP of the LCPs of this and this, this and this, this and this. That's what we were looking for. And so obviously you can do it in time O of the length of the range, because look at all these LCPs. We know how to find LCPs in time O of 1, and you just choose the minimum. But they showed that you can do this in pre-processing time n times log squared n log log n, and then you have the extremely fast query of O of log n log log n. So that was the problem they considered. So we said, what about if you don't have this point out here? What about if you just want to pre-process so that given a range, what is the maximum LCP of any pair within the range? Yes. So this is like a worst case for all the ranges. Obviously, if your range is smaller than log n log log n, you may as well just go and do the brute force, yes. So one would tend to say that the query time would be the minimum of the range and this. So that's yes, good point. So we were saying, what about the maximum LCP between two ranges, or even within a range? So what I'm going to concentrate now in the continuation is we have one range, I want the maximum LCP. So obviously, you can do it in time O of the range size squared, because check out all the, so it's not even written here. So the naive way we could have done it is no pre-processing and O of d squared, because here the d is the length of the query range. So not written here is no pre-processing and O of d squared query. Okay, so that would be the naive, right? Everybody agrees. We know how to find the LCP between 2 points in time O of 1, and so do the LCP between all the pairs and choose the minimum. Okay. Now, so what we're going to see now progressively are different kinds of algorithms that are better than that, and they use a bunch of the stuff that we learned, including suffix trees and LCAs and periodicities. And the nice thing about this is that every one of these things, and range minimum queries, and even orthogonal range queries, which we haven't used for anything, but it's a good opportunity to show what that is also, because that's a tool from computational geometry. So this is nice, but so let's write here, so only so that we have the very naive algorithm. So no pre-processing. Or rather, not no pre-processing, no special pre-processing, because you'll need pre-processing for the LCA, but no special pre-processing. And O of d squared query. And that would be by doing all the possible LCAs. Okay, so what we're going to see is that we can already, in some sense, improve that, or not improve, it's the same work, but if you do O of n squared pre-processing, then your query can be O of 1. And that in itself is we'll need to see how we do that. But because even if you look at all the n squared, the naive way, if you want to build the table of n squared size, but in order to fill it, if you're still going to need to do n squared for every one of the tables, you're going to get to n cubed preprocessing. So this improves it by saying we can do a O of n squared preprocessing and O of 1 query. Then we're going to show that with O of n preprocessing and O of d log n work, we can actually, if you just preprocess in linear time, which seems like a reasonable thing to do, then in O of d time you can do it. And here what you save is that you went down from d squared to d. And then we're going to show that, in fact, with no preprocessing, no special preprocessing, we can get an O of d algorithm. But this one only gives you what is the pair that has the longest LCP. It doesn't really give you the LCP itself. So if you really want to do that, you're going to then take the pair and do one LCP query, which is another O of 1. But we can do that and give you that pair. And finally, we're going to show how we can do it in O of n log n preprocessing, and then in O of log n time. And again, I will add your proviso that log n is smaller than d, because otherwise, yes, you can use one of these guys. All right, so let's start. The first thing we're going to see is this one. How can we do that? So we want an O of n squared preprocessing. The first thing that we're going to do is to preprocess for the point LCP. That's the LCP that we all know. For any 2 points, we can find the LCP. The point is, the point. So what we need to keep in mind is that, yes, we can construct an n by n table where ij has the LCP of SISJ. But what we want is going to be a range. So how do we deal with these ranges? Okay. Well, remember range minimum queries? So what did range minimum queries say? Range minimum queries said that you can preprocess a string, and then when I give you a range, it gives you the minimum of that range. Well, what happens if I want to do it in 2 dimensions? So I have a matrix, and when I give you a range, you find the minimum in that range. Well, the answer is that it is possible to do 2-dimensional range minimum queries also. That's a paper by Yuan and Atala. Does it say somewhere? Yes, Yuan and Atala in 2009. So you can, in fact, preprocess. That was nice because we had the paper, Moshe Levinstein and Johannes Fischer and I had a paper that could preprocess in time n log star n, and then these guys came and very nicely showed that you can preprocess in linear time, and then when you do a range minimum query, it gives you the minimum. But the fact is that range maximum and range minimum are the same algorithm. It's just that you exchange the minimum for the maximum. Everything that we did for the range minimum, and in fact, everything that any algorithm does for any range minimum is the same as range maximum. It's just that for every one of these ranges that you precompute things, precompute the maximum, not the minimum. There was nothing about the minimum that was crucial. And that's why what we need really is when you're looking for some range. So they know how to do the maximum LCP in ranges I, J, and KL. And that would be the maximum number in the range. But when we want the range in ij, then it's not ij by kl. So the range that we're asking for is ij by ij. Find the maximum, and that is going to be the maximum LCS that you have in that range. Okay, so that solves the first line. Is everyone happy with this solution? So we'll move on to the next one. Let's see what that one was. Okay, so now we want to do O of n pre-processing, and then the query in time O of d log n. Okay, so now we're going to have a linear time pre-processing. All right, we're going to now do something else that we have done before and we love to do. Consider this string and look at all its suffixes. So these are the suffixes of the string, except we're not going to build a suffix tree. What we want to do is sort these suffixes lexicographically. So let's sort them. So these are all the suffixes, but they're sorted lexicographically. Now, I haven't shown you how to do it, but this is also what is called the suffix array sometimes. So it can be done. And there are algorithms that know how to do this in linear time. No. I think Karkinen and Landman from 2004 or something know how to do this in linear time. In time almost linear, it was known well way back. There was a Manber and Myers algorithm from SOTA 1 that actually did suffix array, but it was in time O of n log n. But the point is this. We know how to take all the suffixes and sort them, and so we sort them. But now that we have them sorted, let's look and see something interesting. Within the sorted suffixes, the closer they are, the greater the LCP. Why? Because if you look at the LCP between this and this, it's obviously going to be at least as long as the LCP between this and that. Because they're sorted lexicographically. So obviously anything in between is not going to be any less. So any two of them that are adjacent, so if we look at these two, the LCP here is of length 4 because this is where they are different. But if you go one more and you ask yourself what's the LCP between this one and this one, it's already only of length 2. It's AB. So while these guys have length 4, these only have length 2. So in short, what we are looking for is really the longest LCP in a range. That's what we're looking for. And so if we know that these were the LCPs within that range, then obviously if we want the longer one, it's going to have to be between two pairs that are adjacent. It can't be between two elements that are not adjacent. But between two pairs that are adjacent, it means that if we had all the LCPs of a particular range, and if we sorted them, then we don't need to really check and d-squared LCPs, because anybody who is far from each other is obviously going to have a smaller LCPs. All we need to check is LCPs of adjacent pairs. So we only have O of D LCPs to check. Okay, let me draw this. So we have some range. And we want the longest LCP in this range. So it means we need to find some I and j such that their LCP is longest. Okay, if we had all the LCPs in this thing, if somehow let's say if we looked at all the LCPs in this range, then in fact, if we knew which one is smaller, which one appears closer to which one in the initial, which suffix, sorry. If we look at all these suffixes and we know which suffix is closer to each one, so let's take all the suffixes here between I and j, take all of these suffixes and sort them lexicographically. To find the LCP is between these suffixes, right? So to find the LCP, if they're sorted, I don't need to check the LCP of these two. Let me check the LCP of the first one and the second one. And the LCP of the first one and everyone else is going to have to be less than that. So I don't need to check it. So let's check the LCP of 1 and 2, then the LCP of 2 and 3, 3 and 4, 4 and 5. So how many LCPs are we checking? We're only checking D LCPs and not D squared. In what? In which? Yes. Mm-hmm. I don't know what's the, because again, you're talking about ranges. So what you need, the reason that the suffix array helps us, that the sorted suffixes help us, is because they'll help us sort the suffixes within our range really fast because they're already sorted. So we just find out where they are, and that's the sorting. So we get already the yes, yes. No, I don't. The question is it going to help in a better way? But in this particular case, the lexicographic order is only so that we can sort it in a manner that gives us the LCPs in the order that we want. Okay. So what we're going to do is build the suffix array. That's Karkinen and Sanders. Yes, they told us how to do that in 2003 in linear time. We process the suffix array for LCP. Kasai had a nice algorithm for that in 2001. So at that point, when we have our query, all we need to do is grab the D suffixes, SI through SJ, and look at their locations in the suffix array. So we produce SK1 through SKD. So we sort them, and at that point, all we need to do is in SK1 through SKD, do the LCP of all these pairs from the left to right. So the first pair, 1 and 2, 1 and 2, meaning SK1 and SK2, then SK2 and SK3, SK3 and SK4. So we have only D LCPs to do. So that gives us the second algorithm. Now, the one where we said no pre-processing, so if you want actually the longest LCP, you're going to do the point LCP pre-processing. But we, without any LCP pre-processing, we're going to be able to, in time O of D, find the pair. And how we're going to do that. So let's now look at the suffix tree. So if you have a suffix tree, and that's that is fresh in your mind because you saw it just yesterday. So if you have a suffix tree, the lowest node that has two children is going to be the LCP of any 2 points in the range of that suffix tree. And why is that? Because that means that the LCP of these nodes is the entire path, right? And so if the entire path is the LCP of these two nodes, and that's the lowest node that has two children, so that's the longest LCP. So that's trivial, or elementary, dear Watson. All right, yes. So the problem is that building a suffix tree takes time O of n and not O of d. Because if we actually wanted to spend time O of d rather than O of n, then we can't say build the suffix tree. Yes, if we took the range and we built the, yes, if we wanted the longest common prefix of the entire, of any pair in the entire thing, we could find it this way. But to build the suffix tree is O of n. So that isn't going to work. So our solution is going to be, yes, we're going to build the short suffix tree. So we're not going to build the suffix tree of the entire tree, but when you get a range ij, build the suffix tree from I to I plus 3d. So that is still O of d, the pre-processing time. So your time is to build the suffix tree is O of d. So we built it. Now, there are two cases that can happen. So we don't have the entire suffix tree, but it may actually already give us the solution that we want if we're lucky. Why? Because if the LCP of all the pairs in this interval are within the length 3 substring, then we're done. Because we take the longest one. Okay? So the longest LCP of nodes of this interval is going to be the one that we want. Let me draw this. Should have left it there. So we built the suffix tree of I to I plus 3d. So we have this suffix tree. Now, of all the, we're going to look at the longest node that has two children, one of which is that both of them are within ij. So the longest node that has two children, both of which are within ij, that is going to be your suffix tree, your longest common prefix. So those are going to be the two elements that give you the longest common prefix. And at that point, we're done. So just go over all of these nodes in the suffix tree. Suffix tree has O of n nodes. Look for each node at its two children. If they're both within I and j, look for the longest node that gave you that. Okay. So far, so good. But, so in this case, we're done. The lowest node that has two children from ij is the one we want. We know how to do that. But what happens if the LCP of all the pairs in the interval is longer than the length 3 substring? In other words, in fact, there were a number of elements whose LCP extends, in the original string, extends beyond this border. So we're not going to know that. I mean, we're not going to know where it ends because we didn't do it. We didn't build the suffix tree, so we don't know where that LCP ends. I'm looking for the max LCP of all pairs. And the max, I guess I should write max LCP. So the max LCP of all pairs is longer than the length 3 substring. Let's write it down already. So why is it blue? I don't even know why I saved it, but okay. Okay, so the max LCP of all pairs in the interval is longer than the length 3 substring. And so at that point, we don't know how far it extends because we did not construct the suffix tree of the entire thing. And if we did construct the suffix tree of the entire thing to find out what's the max, what is the max LCP that has children from I and J, would mean O of n, because we would need to kind of look at all of its nodes in order to see what node actually has children from IJ. So it seems like we are stymied here, but except for one thing. So, okay, so we have a problem since the length is not in our tree. But what does it mean? It means that the longest LCP, one of its children at least, is a dollar. So it means it goes on. So it's a dollar. There's nothing else. It's not a continuation somewhere, but it actually has dollars as its children. So the lowest node would have a dollar as a child, which means that this thing actually goes on. And past this, it could go on, and we don't know how far it goes on. Now, we also know something else, that the length of the LCP is greater than 2D, because we started here in the first D, the suffix tree went on for 3D, and the LCP actually extends beyond that. So it means that the LCP is in fact longer than 2D. So at this point, we get into something that we spoke about a couple of days ago, periodicity. So I told you that one of the things that people who deal with periodicity know intuitively is that if you have a string that overlaps itself and it's equal, so this is equal to this, and the overlap is within the first half, so you know that the string is periodic because now this is equal to this, and then because that's the second one, it's equal to this, and then the third one is equal to this, so that's a period. So what does it mean in our case? We have a string overlapping itself. The overlap here is, because that's the LCP, so the overlap here is the fact that it's the longest common prefix. It means that this is equal to this, right? So the overlap means that what we have is a periodic string here. So that's the situation. We have a periodic LCP, and it extends. However, the longest period is also, the longest LCP, the longest one that has a dollar as a sign, is going to give us the shortest period. So it's going to enable us to identify the pair with the longest, so we have the longest LCP, one of them is $1, and it has other children. So we're going to choose the child whose index is closer to the dollar suffix. And by the periodicity lemma, this is going to be the period that is the smallest, so it extends the most. And that's the pair that you want to choose. Now, if you also did a pre-processing for point LCP, at this point, take these two INJs, run them through a LCP query, and you're going to get the longest LCP as well, and not just the pair that gives you the longest LCP. So far, all of these cases were warm-up cases because there wasn't really any new idea here. All we did was we used stuff that we had learned before. And I actually like that because I felt that it's a good, a fitting close to end of this course. So let's see a problem where we can have many solutions in which we use many of the techniques that we had dealt with. But now let's look at a new idea. And this new idea is called the idea of bridges. So you look at a bridge. What's a bridge? Let's say that I and j are two indices. They're going to define a bridge. The length of the bridge is j minus I. The height of the bridge is the LCP of SISJ. So by that, we define a bridge. So when we say that we want the longest LCP within some range, so what we're saying is we want to find the highest bridge that is in that range. So the range LCP problem is this. We have a range. We look at all the bridges in that range, and we want to find the highest bridge. Again, the problem is that there are j minus I squared bridges. So we obviously need to somehow clean it up. And so we are going to clean it up by a similar idea that we saw with sorting the suffix arrays. And we said we don't really need to look for the LCP in the sorted suffixes, but we only need to look for those next to each other. So what we're going to say is, okay, in an interval, if we have a whole bunch of bridges, yes, there's a quadratic number of bridges, but we don't really need to look at all of them because some of them clearly subsume others. For example, if we had these two bridges in an interval. So the orange bridge is one that you're going to say, why is it even there making noise? That cannot be the answer, because no matter what range where the orange bridge is, the green one is there also, and it's taller. So I don't need the orange bridge. So any bridge that has in it a taller bridge is already superfluous. Okay? So is that clear, the idea? So in general, before we're going to get into the details of how we do this, but in general, the idea of this algorithm is going to be, let's look at only what we call optimal bridges. In other words, let's throw away, let's prune all the bridges that are not nice, that are not contributing to anything, that are just there, because they couldn't be our solution anyway. And let's remain with the optimal bridges. What we're going to show is that the number of optimal bridges is really n log n. It's not n squared. And therefore, because there are only n log n optimal bridges, then we're going to only deal with them. And that is going to make our algorithm more efficient. OK, so as we said, the orange bridge is never relevant, because everyone sees why it's not relevant. Because when is that going to be an answer? It's not. It can never be the answer. So it shouldn't be there to begin with. OK. So now we're going to start working on creating these optimal bridges. So, and there's going to be a bunch of technical definitions here, so don't worry too much about this. But all of them will have examples. So, and I know that everyone is already tired by now after 9 days of non-stop pattern matching. It's enough to drive an elephant mad. So, okay. So I mean, I know it's driving me mad almost. So, so I1 through IK are indices where the LCP of all pairs is the same, and we keep them in an ascending order. In other words, let's say that what we have is a bunch of indices where the LCPs, so we have, like in this case, it's 1, 4, 7, 9. So we have 1, 4, 7, 9, a bunch of indices that we keep in ascending order, where it turns out that the LCP of any two pairs of these is the same. So in this example, the LCP of 1 and 4 is AB, because here you have a C, here you have a D. So obviously the LCP is AB. The LCP of 1 and 7 is also AB, because this is ABC, this is ABE. And the LCP of 1 and, what was the next one? 10 is also AB, because this is ABC, this is ABF. So AB is the LCP of 1, 4, 1, 7, and 1, 10. But it's also the LCP of 4, 7, 4, 10, and also the LCP of 7, 10. So any pair of these guys, the LCP of them is the same one. So these are the indices in ascending order of these pairs. So the point is this. It already allows us to prune a whole bunch of pairs that we don't worry about because they couldn't be optimal. Because it's enough here to look for LCP of the adjacent ones, the LCP of 1 and 4, 4 and 7, 7 and 10, because everyone else is the same height, but it's longer. So it's going to be non-optimal. So, so for any indices that we have where the LCP of all the pairs are the same, if we keep such a list in ascending order, the only bridges that we care about, the only optimal ones, are the adjacent pairs. And this is, again, similar to the idea of the suffix arrays, but here they are sitting there in the, but here we're looking at it from a bridge point of view, and we're saying they're not within each other. Okay. Now a tool that we haven't seen yet, but that has been useful in a number of pattern matching problems, and that's orthogonal range queries. This is a tool from geometry. In geometry, they say the following. Suppose we have n points in the plane. And so it's a sparse thing. You have these n points, and they're sitting somewhere. You have the coordinates of the n points in the plane. You want to pre-process these n points in order to be able to answer the following types of queries. When I'm giving you an orthogonal range, in other words, I'm giving you some rectangle, and I'm asking the sort of questions like, give me the points in the range. Or, what if these points have values? What is the maximum or the minimum value in the range? So these are the kind of questions. They're similar to our range minimum and range maximum question, except for one thing. The reason this is geometric is the space is not filled with information the way it is with us. When we talk about range minimum in pattern matching, then you really have the entire space is filled with values. And when I give you a range, I want the maximum or the minimum where every pixel has a value, and I want the maximum or the minimum. The geometric orthogonal range queries model is where you have points in the plane. In fact, they also have this in space. Geometers don't limit themselves to 2 dimensions, of course. And it behaves differently in high dimensions, et cetera, et cetera. But for us, what we care about is the plane. So we have these points in the plane. They are sparse, so not all points in the plane have a value, but these sparse points that we have do have value, and we want to pre-process these points in order to be able to answer what is their maximum in the range, what's the minimum in the range, or who is in the range. List them for me. So what do they know how to do? In fact, I think they even know how to do things a bit faster than what's written here, because geometry keeps running on, and we're just using them as a tool. So if they can do things faster, this is going to make this algorithm faster. But at the time, this is what they could do, is given endpoints in the plane, they can pre-process them in time O of n log n, and then they can answer the orthogonal range queries in time log n plus TOCC. The TOCC comes in when you don't want the minimum or the maximum. The TOCC comes where you want the elements in the range. So if there are 5 of them and you want to list them, you're going to need to pay 5 in order to list them. But if all you want is the maximum or minimum, or even how many of them are there, then you can answer it in O of log n. So this is pretty neat. O of n log n pre-processing time, O of log n to answer. As I said, in fact, it's probably, I think it's faster. Yeah, I'm pretty sure. But that's good enough for the moment. Okay, so let's get back to the bridges. We have these bridges sitting here, and suppose that we only have the optimal ones. What we want to do is to find the highest optimal bridge in the interval. Now, notice these kinds of constructs that look like a Roman aqueduct, they are the ones that come from the kind of situation that I showed you before with those 1, 4, 7, 10, because they're the same height. So in fact, you're looking for this bridge and this bridge rather than the third bridge gets lost. I mean, you don't need to look at that. So what you have is these aqueduct type of things. And here you have also an aqueduct. So this bridge itself from here to here is not optimal for 2 reasons. It's not optimal because of this, that is taller. But it's also not optimal even if this one wasn't here, because it can be split into 2 bridges that each one of them exists in its entirety in another range. So what we have here are optimal bridges that basically are like aqueducts and then taller or shorter, except this one is not a good bridge for us because it's outside the range, and this one is not a good bridge for us. Which one is that? This one, I guess, is not a good bridge for us because, again, one leg is in the range, one leg is outside the range. So of the optimal bridges within the range, the answer we would like is this one because that's the tallest one. So that's what we need. We want to find the highest optimal bridge in an interval. Okay, so let's give an algorithm now that assumes that there are B bridges altogether, and then we're going to show what this B is. So assume that there are B bridges. So B is the number of bridges, of optimal bridges altogether. So let's denote a bridge xy as a 2-dimensional point. So on coordinate x is going to be the first, a bridge xy is going to be the point that you get in coordinate x and y, but the weight that that point is going to get, the value that it gets, is the height of the bridge. Now, we're going to pre-process all of these B points in time O of B log B for orthogonal range queries. And then the query time is going to be O of log B. But what does the query tell you? So you want to know what is the tallest bridge within the range. Okay, now, all the bridges are now points in this 2-dimensional space with a weight. If I want the maximum within a given square, Well, what I'm going to get from that square is within this range, who are the points that are both legs are in the range, and I'm going to get the maximum. So it's going to give me immediately the bridge that I want, the highest LCP. Yes. Yes. How do you know that both legs are inside? Because so it became two-dimensional, the whole thing. So if I am looking for a bridge from I to J, sorry, if I'm looking for a bridge that's in index X and index Y, okay? So that's the bridge. So basically, this bridge is the LCP, but fine. So I'm going to write XY, and in XY, I'm going to write the height of the bridge. So in fact, the LCP. And so let me draw here some sort of range just in order to make things easy. So we have here a Z. Okay, so this was XY, and now we have a YZ, let's say. And we have the other LCP. And let's also draw here this guy, that W and Q. Okay, so we have a W and we have a Q. And we have here an LCP. So let's concentrate now on these bridges. But what's the range? The range is IJ. So this would be I, this would be J, and this would be I, and this would be J. So this is the range that we're looking at, this area. Now, all the bridges that are inside are going to be points inside this range. And so if I get the maximum, I got the tallest of them. Now, suppose I had some bridge here, Q, whatever, R. Well, then it's true that I would have here the Q that's inside. Q is between Z and Y. Q. But the other is below the J. So in fact, the point is going to be here. So any bridge, one of whose legs is inside, but one is outside, is going to be within the one dimension of this square, but it's not going to be in it because the other leg is outside. So the bridges that are in here are precisely the bridges that we care about. The orthogonal range query is the box whose corners are II, JJ, IJ, and JI. So that would be the range query. So the idea here basically revolves around a simple concept. The concept is that we need to prove that there's a small number of optimal bridges. And once there's a small number of optimal bridges, pre-process it for the range query, which is fine. Your pre-processing is going to be O of B log B. Your query time is going to be O of log B. If B, for example, would have been N, so you have an N log N pre-processing and log N query time, and you get your maximum LCP. So in a few minutes, we're going to talk a little bit about why there's actually a small number of these bridges. And what I'm not going to talk about, because that's another paper by Apostolico and Preparata, in fact, how to find these bridges in an efficient way. But the point is that that here what we have is actually a new idea, like I said, as opposed to what we had before, where we didn't really have any new ideas, but we had clever use of ideas that we knew in order to solve the problem. Here we have a new idea, and we're going to say, okay, we still need some tools, some fancy tools from geometry. From here to there, we borrow it. But the point is that we're going to narrow down our object in a new way. And the way that we narrowed down what we needed to, the types of LCPs that we did before, we narrowed it down before to D. Now here we can narrow it down globally to n log n, it's going to be. And therefore, using the geometrical range queries, it gives us the solution that we want, which is independent of the D. And again, if D is smaller, then do the D. Okay. So we're going to be doing a max query on the range ij. That gives the highest bridge. So what's left really here is to show that the optimal number of bridges is no larger than O of n log n, and that the optimal bridges can be calculated in time O of n log n. At that point, we're going to get pre-processing of n log squared n and a query time of n log n, of log n. So that is what I promised. And like I said, this is current knowledge in geometry makes it better. I think it's a bit better. So this maybe should have been written as a function of the time it takes to pre-process for orthogonal range queries and do it. And then it will be good forever. You just plug in. As they improve, this algorithm improves. As they improve, this algorithm improves. Okay. So, you know what? Let's break here, and we'll do this proof after the break. Excuse me? In the pre-processing? Here? So we have n log n bridges, and so the n is n log n, and then you have log of n log n. So log of n log n, you're right, would be log of n. But here you have n log n. So n log n times log n is n log squared n. Okay, so the time is the number of bridges times log of the number of bridges. But if the number of bridges is n log n, then this is not n, it's n log n. N log n times log n is n log squared n. And there's also this log, but that is a plus, and it gets reabsorbed in the big O. But the log n is there. Okay? Clear? Okay. So let's